Okay, here's a first order linear recurrence problem. We've got the size of a population of feral cats can be represented by the recurrence relation Pn plus 1 is equal to 0.8 Pn plus 50. So we can see that this is first order linear recurrence because we're multiplying the previous term by 0.8 and we're also adding 50 to it. And we've got our P0 value of 76. So first of all, determine the size of the population after 1 month. That's pretty easy. So that'll be P1 is equal to 0.8 times by P0. Now P0 is 76. And then we add on 50. And we can use our calculator to work that out easily enough. Let's go into main menu there. Edit clear all. And our calculation was 0.8 times 76 plus 50. That gives us a population there of 110.8, or approximately 111 feral cats. After 12 months, easiest way there is to go to sequence menu. So if we go to sequence menu, I'll just pull up my menu here, go to sequence menu. I've already got the sequence in there, so AM plus 1 is equal to 0.8 AM plus 50 with A0 equal to 76. Just tap on the little table there. And well, I've just got to see here it's starting at n is equal to 100. So I might go and change that by going to this little button here, the XY button. And I'll go from 0 up to 12 months. So okay. I can scroll down here and see that after 12 months, we're up to 238.04. That's pretty easy. So P12 is 238, whoops, try that again. 238.04 feral cats. And because you want integer values or whole number values, feral cats, you would say 238 cats. Now, comment on the size of the cat population in the long term. This one here, if we're looking at the actual recurrence relation here, we can see that each term, it's the previous term times by 0.8 and also 50 added on. So just by a quick glance at it, we're not sure whether the population is going to be increasing or decreasing. But we can see that in terms of our answers so far, P1 was 111, P12 was 238. So, it appears it's increasing here, but it says comment on the size of the cat population in the long term. The question is, will the 0.8 PN here mean that the population will reach some steady limit? Now, we're not sure, but what we can do is just go to sequence menu and pop in some kind of large values. So again, back in sequence menu here, if I click into the table and then I go to this little button, the XY button here, and I might just go from 0 up to maybe 100 and just try that out. Now, because I'm putting quite a large range of values, 0 to 100, it might take a while to calculate. So it didn't take too long. So we can sort of scroll right down as we get a bit further down. It looks like around about 17, 18, it's sort of heading towards 247, 248, getting closer and closer to 250. And in fact, once it gets to 250, it sits there and doesn't change. If we click on one of those values, you can see that it almost gets to 250, but not quite. So what's happening there is it's just approaching that value of 250 feral cats. So in terms of comment on the size of the cat population in the long term, we could say it's going to be steady state, 250 cats. So the steady state just says that it does reach a steady amount of cats, 250 cats. And what we'll notice there is if we actually went and subbed this 250 back into our recurrence relation up here, just wait for that to clear up. If we went 0.8 times 250 and then added on 50, we would get 250 again. So once it hits a population of 250, this recurrence relation will just continue to remain at 250. Okay, the last part of this question, part B, says we've got another population of 24 feral cats was observed to grow to 44 after 1 year and increase to 74 after 2 years. The size of this population can be represented by, okay, so we've got a first order linear recurrence relation here. Pn plus 1 is equal to R times the previous term, Pn, plus K, and we've got this P0 value of A. Okay, so for this one here, we want to find these values of R, K, and A. Now, I guess the first thing to note here is that this A value is the P0 value. So that is, in fact, our initial amount of feral cats, 24 feral cats. So straight away we can say that A is equal to 24. Now to get the values of R and K, what we can do is just substitute the values we've got. So starting at 24 feral cats, growing to 44 feral cats, we can substitute those first two values into our recurrence relation here. And we can say that P1 will be equal to R times P0 plus K. Now we actually have the P1 and P0 values. The P1 value after 1 year is 44, the P0 value is 24, so we can sub those values in and get 44 is equal to R times P0, which is 24, plus K. We've there got one equation for R and K, and because we've also got population after 1 year and population after 2 years, we can do a second equation, which will be P2 is equal to R times P1. So P2 is equal to R times the previous term, P1, plus K, and substitute in the relevant values here. P2 is 74, is equal to R times P1 is 44, plus K. And we've got a second equation. Now what we've got here is two equations, equation 1, equation 2, and we've got two unknowns, R and K, so we can solve those two equations simultaneously, and the calculator does that very easily. So if we go to the class pad here, what we can do is pull up our keyboard, and you'll see on the keyboard that down over here, I might just go back to main menu perhaps first of all. So I'll go click back on main menu. In main menu I'll bring up my keyboard, and maybe I'll get rid of whatever's in there to start with. So I'll go edit, clear all, okay. And then on the keyboard under Math 1 tab, we've got this little button here, or this function here. That's the simultaneous equation solver. So we can go put our two equations in there. So the first one was this equation here. Now, just for ease of entry, what we can do is we can put in x for R and y for k, just to make things a little bit easier. So I'll pop that in there. It'll be 44 equals, I'm going to use x instead of R, times 24 plus y. There's my first equation. Second equation was this one over here. I'll pop that one in as well. And we've got a bit of a shadow going on there, that's all right. So that was 74 equals x times 44 plus y. And we need to tell the class pad that we're going to solve for x comma y, and then just hit execute, and there it is. It gives you the answer straight up there. So we've got, now the calculator gives x is equal to 1.5, but remember the x values we're inputting for the R value, so it would actually be R is equal to 1.5 and K is equal to 8. So there's our final two answers there. So we can say that recurrent first order linear recurrence would actually be Pn plus 1 is equal to R value 1.5 times Pn, and then plus that K value of 8, with of course P0 being equal to 24 there. Now we can check this on these values. We could check it, for example, for P1 there. Now P1 should come out to 44. So if we did that, it would be P1 is equal to 1.5 times P0. Now P0 is 24. plus 8. And doing that little calculation there, we'll get P0 is equal to, P1 is equal to 44 as expected. So that's just a little check I've done there, not really necessary. But we have our final solution there of, I'll just write them out as a final solution. A equals 24. Oh, what happened there? Get rid of that. R equals 1.5. K equals 8.